Hello, everyone. Let's start with the presentation of today. We talk about elevating curtain wall performance with fiberglass framing, presented by Sustainable Project Group and GlasCurtain. Agenda of today will be an introduction about ourselves, a little bit talking about the current situation, problems and approaches, and then go deeper in fiberglass framing. And during the presentation, feel free to ask questions, and there will be some poll questions to educate everybody. So presenters of today will be myself, Robin Lucidarme, Business Development Manager, and Peter Dushenski, Managing Director of GlasCurtain. Let's introduce a little bit why we had this presentation today. We need to live more and more in net zero buildings, and we want to avoid living in a stranded asset. But it's a little bit complicated because first of all, we have our existing building stock that we live with, and there's a lot of different things coming towards us. But let's explain the way how to approach and how to get to a net zero building. First of all, net zero building, how do we see that? Net zero building, we mainly focus on operational carbon, but don't forget that also embodied carbon is an important aspect to cover. And how do we cover all these topics? We will go a little bit deeper in modern construction methodologies, low carbon supply, and then in the operational carbon, low energy use, measurement and verification to check if the implementation performs like it's needed, and going in the building operations. So that's for us a net zero building. Why do we explain that? If we want to hit our targets 2030, 2050, we see that the majority of the buildings, like 50% of the buildings, will still be there in 2050. And to hit our targets, there's two strategies. We can or start with new buildings, tear it down, and then lower our emissions with 500,000 tons per square meter, or we can use our existing buildings and do a deep energy retrofit and lower our emissions even more. It's a little bit also complicated. And why do we do that? We say, look, if you look at the buildings, you can see here 70% is going in operational carbon, but don't forget that 30% is also in the design and build. So that's why we wanted to go a little bit deeper in the technology of GlasCurtain as well. So if you're a property manager or you manage a lot of buildings, the question is, do you have your class A, B, C, or D buildings? What are you going to do with it? Are you going to do a new build or renovation? And every type of building type has its advantages and disadvantages, but this is the situation we live with. And that's why we try to create strategies with the current technologies that are available on the market. What is pushing the agenda to upgrade all these buildings? There's a lot of different things that happen. So for example, we have the carbon tax, and then we see in Vancouver, for example, we have the GSGI index that has also been used in different states, like the local law 97 or BERDU or BEPS, where your building get an energy score, and you also need to report emissions, for example, commercial buildings larger than 50,000 square foot or multifamily larger than 100,000 square foot. So your building gets an energy score and indirectly gets also a property value. We see that these values are sometimes difficult to get to report, but you see these values are imported in the Energy Start Portfolio Manager and directly reported to the city. Okay, what does that mean? So a typical building is using electricity, gas, and also water. But here we see in an energy audit that we have energy that's used, ventilation, lighting, cooling, and then lots of energy in the boilers and make-up air handling units. And we want to lower that as much as possible to avoid these penalties and lower the carbon tax. But we say if we want to do that, we as a stakeholder in managing buildings, we need to look at on a different way. So how do we say that? You can approach it a static way or a dynamic way. And we want to go a little bit deeper in here. So the majority of the people, and sometimes we do that, but we try to adjust our model, is we say our utility data is, for example, a $900,000, but we keep that flat. But we know that it's not going to stay flat. If we add carbon tax, penalties, and inflation cost, we will see our utility cost is not going to stay 900,000. It will go to $1.5 million. So that's a different approach, and that's more the reality. On top of that, what is our industry trying to do? For example, imagine we want to reduce our emissions with 30%. So we will implement energy conservation measures, better windows, better insulation, heat pumps, and so on, to lower our utility data from 900,000 to 700,000. And because we implement these energy conservation measures, we will have an avoided cost of $1.6 million. But if we know, when you see these bars here, where we will add carbon tax, penalties, and increase of utility cost, we will have our utility data from 900,000 to $1.1 million. So that's different, but our avoided cost will be $3 million. That's already pretty good, but we don't hit our 30%. We only hit 26%. And that's creating more penalties, and we want to avoid that. So how do we want to do that differently? So we need to look at the dynamic way, and the dynamic way is we immediately calculate carbon tax, penalties, increase utility costs. And because we do that, we have a better model, and we want to keep our emissions lower. So we still start from 900,000. We at the end still stay at 900,000, but our net operational income goes up 11%. Our value of our property increases approximately 40%, and our net present value also increases 3 times. And our reductions is 50%. So we hit our 50% reductions, and we avoid a total cost of $4.1 million. So that's the scenario. And how does that work in reality? Normally, you do an energy audit and you look at the energy conservation measures you want to go implement: lighting, lighting controls, building automation, work on the building envelope, VFDs, and so on, like everybody knows. We take all these measures and then we bring them in a typical spreadsheet, and we'll look at them from a payback point of view. We sort them from fast to slow. And then we will see that we will only implement the payback that is 3 years to maybe 5 to 6 years. But if we look at this model, we see that the project cost stays low, net present value is low, but our GHG savings is only 13% to 14%. So we don't hit our numbers, even though we need to hit our numbers 30 to 50%. So another approach could be look at net present value, and then we see that everything that stays positive, we have a net present value. We see that a lot of more projects are now being considered to do, but still not all the projects are being done. And if we look at the math here, you will see that with this kind of projects, you will hit approximately 30%. So it's better, but still not your 50%. Let's explain that a little bit in a real project, how to look at, instead of payback and net present value, to look at adjusted present value. Adjusted present value is, for us in Canada, we look here with adding the carbon tax per ton. So we will add an additional $4,000 to $5,000 per ton. So how does that look in the reality? So I have a couple of examples, but I wanted to keep it short. So for example, let's say we're going to invest in the building envelope. So we will do insulation, windows, and upgrade the roof. and we spent for that $1.9 million with a saving of approximately $27,000. Payback, 66-year net present value, $1.1 million negative. So very bad, where we won't consider that project. Okay, let's add a little bit of solar wall here. So we add more CapEx in this project and we increase the CapEx, but we have more savings. Because we have more savings, we have a better savings. Our payback is better and our net present value is also better. Okay, if we look at the next step, we know if we increase our building performance, so we don't have such a leaky building, that we know we can actually underdimension everything a little bit more. So instead of 1.9 or $2 million, we can go to $1.8 million, have a better savings, better payback, and better net present value. That already looks way better. But here we go to, from net present value, we start going to the next thing where we look at adjusted present value, because you need to add the financial aspect also. And you can see the savings that we had here is the $36,000 is completely eaten by the penalties and carbon tax. So that means that the payback stays the same, but my net present value looks also much better. And so if I look to the next scenario, is if you start, for example, investing in $1.8, $1.9 million and you go to a traditional bank, you will see that your loan will be between a 4 to 6%. But if you use green loans, for example, so instead of lending from a 5 or 6%, you can lend a 1 to 2%. So your savings, your better financial model generates the same payback, but your net present value suddenly looks way better. And so why I introduce that, because if we want to hit our 30 to 40%, it's very important to look at these kind of models and have a better idea why to go for building envelope, windows, insulation, and so on, who have a lower payback. But if you look at this way, there's a better way to implement these projects. So, and that was for me the perfect introduction to go to the slides from Peter.
Thank you very much. My name's Peter. I'm, yes, the managing director of GlasCurtain. So today we're going to explore some of the most exciting advancements in building materials and how we can better future-proof our building facades. Specifically, we're going to look at next generation high-performance building materials and how they're transforming what's possible in the construction industry. And so we'll take a look at this from an energy efficiency perspective, from a carbon perspective, as Robin has done a great job of talking about already so far, as well as also from an architectural and aesthetic perspective, and then really just from a long-term perspective, which again is part of the financial conversation, part of the carbon conversation, part of the whole package. And all of this is really critical to what we'll call as future-proofing our building facades. And by this point, you've probably said, the word building facade enough times that we should probably define our terms. I know we have a very broad audience here today. So a building facade is really part of the building envelope. And the building envelope is basically the skin of the building, everything that's on the outside. You can sort of imagine that, our buildings are like bodies, right? And there's a skin and there's a skeleton. The outside is the building envelope, also called the building skin, and that's really the roof, is the sort of top horizontal aspect, the facade, which is the vertical aspect, and then there's, of course, the foundation underneath. Today, we're going to really focus on the vertical part of it, and that's really because this is really the defining part of the building in so many ways. It's the defining part from an aesthetic, from an architectural perspective, but also in terms of how it impacts the occupants. Because after all, a facade, it has the same root word of face, right? And so, this is our representation, to the world, but also how our buildings make us feel and how it allows us to be sort of, healthy and productive, and make sure that, our buildings and ourselves, that we look good and we're doing good work at the same time. So let's dig into all that is high performance building facades. And so, what are some of the jobs that we're asking our building facades to do? These are hardworking parts of our buildings. And there are several ways in which the best facades differ from our run-of-the-mill facades, the sort of average kind of stuff that's, very conventional. The best stuff really is a cut above in these categories. So number one is definitely energy efficiency and sustainability. So in most of Canada, and definitely in the colder parts of Northeast United States, better building facades mean better R values or lower U values. And Robin asked me to sort of again define my terms here. What are R values? What are U values? Why are these things important? So R values are really the insulation. The way in which we measure insulation values. So a higher R value means that you typically have thicker insulation or better insulation. So it's kind of like, the higher the R value, the better your sort of like your jacket is rated to like a minus 10, minus 20, minus 30, minus 40. The higher the R value, the sort of warmer your jacket is. You can kind of think of it that way. Suffice it that in our colder climates, especially in Canada, especially with rising energy costs and increasing cultural emphasis on environmental concerns and regulatory emphasis on environmental concerns, we now can use innovative materials to improve these insulation values, to sort of be our warmer jackets, and to create building facades that better maintain a consistent internal temperature, which will then drastically reduce the need for heating and cooling. And really, this is the whole passive principle. And we've probably heard of this term being thrown around increasingly, I shouldn't say thrown around, being used, in very valuably, increasingly, is the passive building or a passive principles. And some of this is, started in Europe, which actually really started in the Saskatchewan Conservation House, which, we can get to that maybe another time. But the idea as we know it today of what are passive buildings can really be applied to all buildings. And that's really just to emphasize the quality of the building envelope and the reduced stress and emphasis on mechanical and active mechanical systems. So we're investing in our building envelope so we don't have to, stress and wear and tear and have these expensive mechanical systems that will break down, that require a lot of labor, to fix and maintain, and parts from, all over the world. That when we invest in a better jacket, as it were, we need to, rely less on these sort of active parts of the building. So it's active versus passive. For the last 50 years, when energy was cheap, when no one was worried about carbon, we just kind of threw more mechanical systems at almost every problem that we, faced from a building sort of science perspective. But increasingly, with more and more emphasis on sustainability, the passive approach, whether or not we're certifying our buildings to passive house, makes more and more sense. And there's a lot of energy codes now, across a variety of jurisdictions that are starting to basically, if not implement the passive principles, they're shadowing it essentially. And this is, whether it's the BC Energy Step Code that is saying, okay, over a 15-year span, we're going to go from here where we are, all the way up to basically shadowing passive house. And we're going to, ratchet up the steps, so over 5 steps over 15 years. Or you have something like Toronto Green Center, Massachusetts Energy Stretch Code. If any of you have seen a little bit, or Local Law 97 in New York, these are increasingly looking at, how do we future-proof our buildings? Because, we're constrained by how much utilities, we can create. We're constrained by, how much energy we can produce, and our populations are growing. And then we're also seeing, of course, that's just on the regulatory side, on the sort of minimum side. And let's never forget that the building code is the least you can do without going to jail, right? This is not like a high bar for by anyone's standards. This is the least you can do without going to jail. The highest, are the voluntary standards. That's the LEED, the WELL, that is actual passive certification, net zero certification, living building challenge. All of those are also looking at, of course, how do we future-proof our buildings? How do we make them more sustainable within our communities? A lot of that circles around energy efficiency and some other sort of aspects of energy efficiency that we'll touch on in a moment. Durability and longevity. So building facades also need to again, withstand the test of time from an aesthetic, but also from a maintenance perspective. So as such, good building facades, which are to say what we'll call sort of high performance building facades, are not only beautiful, but also use materials that are resistant to condensation, corrosion, and temperature extremes. And so this durability and longevity in high performance building facades reduces the need for maintenance that the facade materials themselves, as well as, again, the active mechanical systems need for the long term. It's not hard to see how high performance building facades contribute greatly to extending a building's lifespan. With a shoddy, run of the mill, code minimum kind of building, especially the kind that we've been building for the last, couple of decades, as those materials start to wear and tear, as they have differential sort of rates of expansion and contraction between the glass and the frame and the opaque assembly and the sort of the fixed part of the building, and you start to have air leakage, all kinds of maintenance issues, condensation problems can wreak havoc on a building envelope, and these require premature maintenance. And these create premature degradation of the building envelope. So we all think that we're designing something, we all think we're building something, but how long is it really performing as we've designed it? How long is it really performing as it was originally built? Well, as weather gets more extreme, those building envelopes, those jackets that we're wearing are getting beaten down that much harder, right? And so it really behooves us. It's a great investment to future-proof our buildings with better building envelopes. And this is, for the health and well-being of our building, which are important investments and important assets. But let's not forget what buildings are for in the first place. Buildings are our shelter. They're where we spend most of our time. And so these buildings should enhance the occupant's health. And so building facades have a huge influence on the internal environmental quality and therefore our well-being by controlling air quality and thermal comfort, both of which are directly and extensively, with scores and scores of research, linked to our health and to our productivity, and again, overall to our well-being. So high performance facades ensure consistent interior temperatures, moisture control, and they reduce the infiltration of unwanted external pollutants, right? So when you have a tight building envelope and there's, a forest fire or something, blowing smoke into your building, you can maintain a healthy interior sort of environment. And this is what we all want, regardless of the kind of buildings that we're talking about. So whether it's residential, we want to be healthier. Whether it's commercial buildings, we want them to be healthier. Or whether it's institutional buildings, government buildings, hospitals, university buildings, we all want them to be healthier. Then we have regulatory compliance and market value. And I think, Robin already did a great job, better than I will, better charts and graphs and research than we will touch on in this part of the presentation. What we can say is that in a lot of markets, and an increasing number of markets, high performance building facades are going from a nice to have to a need to have, as the world continues to raise the bar for energy efficiency and environmental targets. So as a result, we're now seeing buildings that anticipate and even surpass these regulatory requirements, more and more of them, to minimize future retrofitting costs and therefore hold higher market value. So in many ways, it's a race to the top, which makes sense because attractive, energy efficient buildings always attract a premium valuation for discerning tenants and buyers. When it comes to technological integration, there's a lot of innovation happening in facades, and some of which we'll talk today a little bit, of course, with fiberglass. But suffice to say that there's a lot going on, and whether that's smart electrochromatic windows that adapt their tinting to changing light conditions, vacuum insulated glass that improves U values or R values with a thinner unit overall. Again, fiberglass materials, all of these have the potential to dramatically enhance the desirability and the appeal of our buildings, and again, to future-proof them. And part of this future-proofing is adaptability to climate change. With the increasing unpredictability of weather patterns, building facades have to perform under arguably a wider and wider scope of environmental conditions. So whereas we thought, okay, we might have to deal, in Edmonton at least, maybe in Alberta, maybe we have to deal with, plus 30 in the summer and minus 40 in the winter. Okay, well, what if I now have to deal with plus 50 or sorry, plus 40 in the summer and minus 50 in the winter. You know, that the scope and the extremes that we could even see in a single day. It's not unusual to see a 20-degree swing in a single day. And what that does to a building envelope is dramatic. I mean, imagine having to wear the same clothes, you know, when it's 0 degrees and 20 degrees, and you have to wear the exact same clothes. You can't change. You can't change what you're wearing. And then now the same clothes we're wearing at 0 degrees and minus 20, right? And if you have to wear the exact same thing all the time, you're constantly having to adjust. There's a lot of adjustment that needs to be done. And our buildings, we're asking them to be fixed assets, fixed products for what, 30, 50, 70, maybe even 100 years, right? That these buildings aren't fundamentally changing their building envelopes. And so that's a lot to ask from our building facades and our building envelopes. And you know, there's much to be done when it comes to improving this compared to, again, the run of the mill. We'll sort of loop back, as we mentioned ago, these passive principles. Let's sort of dig into what are these passive principles and how can we apply these more broadly, even if we're not designing a quote unquote passive house building. Many building codes are starting to regulate, basically, are starting to target essentially these principles, if not in name, then in practice, right? And this is, you know, the BC Energy Step Code is doing this, Massachusetts Energy Step Code is doing this. Those are the two leaders in their respective countries, and others are following. And so what are these passive principles? Number one is enhanced thermal insulation. So thermal insulation is really the cornerstone of passive design. So here we want to use building facade materials with high insulating value, so, you know, warmer jackets again, to minimize thermal bridging. What is thermal bridging? Thermal bridging is when, you know, it's sort of like if you have your jacket unzipped. That's thermal bridging, right? It's like, you know, that the outside is not staying where the outside should be, and the inside is not staying where the inside should be. So you have basically materials that are allowing for conductivity between the inside and the outside of the building. And so, you know, materials like aluminum or metals in general are very good conductors, right? And this is why we use metal for wiring. This is why we use metal for, you know, radiators. This is why we use metal, you know, for, yeah, exactly, on our engine blocks and our motorcycles or something like that, right? Why you have all those fins, you know. This is because we're on those kinds of things, we're trying to dissipate heat. But when we have a jacket on our building and sort of the skin, the envelope, we're trying to actually have better insulating values. We don't want that thermal bridging between the inside and outside. So minimizing the amount of metal that we're using is key to this. We also want to maximize air tightness, which is distinct from thermal bridging per se. So you can have a building with a lot of thermal bridging and very good air tightness, and you can have a building with very little thermal bridging and very poor air tightness. Ideally, we want both. We want low thermal bridging and high air tightness. And these are really the passive principles. And in order to achieve that, you know, we want materials that are low conductivity as well as low differential rates of expansion contraction. So they're not moving apart as much, so that they're all moving together. Basically, if we're going to have multiple materials, which of course every building envelope, you know, there's not a lot of building envelopes that are all one material. I haven't seen, you know, maybe your metal shed or something, you know, in your backyard is all just metal shed. But most of the kind of buildings, whether it's a house, whether it's a hospital, whether it's a school, what have you, there's many kinds of materials being put together. We want them to move together as much as we can. This will, again, maintain air tightness, so that when we, you know, have our air vapor barrier running across these materials, that it's going to stay, you know, connected, and we're not going to have air leakage. Because what is air leakage? Air leakage eventually means that we're heating or cooling the outside, right? If we're having air leak, and if we have basically a sieve for a building, you know, our mechanical system almost has to be infinite, right? You know, infinitely powerful for heating or for cooling. We want to minimize the impact, the stress, the wear and tear on our mechanical systems, because mechanical systems are not only high operational carbon, high operational cost, and parts and labor are getting tougher. And parts and labor, you know, I haven't met anyone recently who's like, yep, in 20 years, parts and labor are going to be easier than they are today. I don't know anyone who's really predicting that parts and labor, for the trades in general, but certainly for things like maintenance, is going to be easier in the future. Arguably, it's going to, it's not easy today. It's going to get harder, and it's going to get more expensive. I mean, even a couple of years ago, it was $150 an hour to have your elevator fixed. Now it's $250 an hour, right? So your mechanical guys are kind of in the same category, right? So they used to be $150 an hour. Now they're going to be $250. Then they're going to be $350. Then they're going to be $450. These should not surprise anyone, when these happen. And so what we want to do is we want to minimize the stress on that mechanical system, investing in that future-proofed building envelope that is going to, serve us the test of time. And this really starts with thermal insulation. If you have like a power outage or something like that, I mean, there's been some great research on how long can you maintain a comfortable interior temperature in the winter if you have a power outage in a conventional run-of-the-mill building versus a building designed with passive principles. And it the curve of the temperature drop in a passive building is like this. So it's like it drops like 2 degrees a day or something like that, and it drops like 10 degrees a day in a conventional building. So when we have a high performance building envelope, it kind of cuts both ways. We can maintain a stable temperature when it's really cold outside, and even when we don't have external heat or sort of internal heat systems, we can maintain that through thick and thin power outages, what have you. So again, this is a future proofing kind of strategy. Number 2 is optimizing solar gain. So one of the key passive design strategies is to really look at, how much radiant energy do we get through the windows and the curtain wall. And this, means that we need to more carefully design the building's orientation, to the best of our ability. Sometimes our site allows for this, sometimes not, but we can always design, sort of where we have our glazing and how we're designing that glazing system. So in the colder months, we obviously want to, maximize the solar heat gain, because that helps to warm our building and, minimize the amount of, again, mechanical systems that we're relying on. And in the summer months, we want to minimize that solar heat gain to, again, minimize our cooling loads. And all of these things are, very ancient ideas. And, as I've talked with John before, who I see was on the call, all of these things are, every ancient culture and tradition has had ideas of, orienting towards the sun and maximizing and harnessing the power of the sun. These are, thousands of years old idea. Every single architectural vernacular you can name leverages the power of the sun to, make it a little bit warmer in the winter and a little bit cooler in the summer. Now we have mechanical systems that, can help to offset some of that, but increasingly we're seeing some of the sort of pitfalls of overly relying on mechanical systems. And so, we do well to sort of look at tradition and look at other cultures and see how they've done it in our individual climate zones. But the third one here is maximizing natural ventilation. And this is, again, another very ancient idea. And this is the idea that we can manage indoor air quality and reduce our stress on our mechanical systems by harnessing natural airflow to allow occupants to self-regulate naturally and to better maintain their health and well-being. And Rem Koolhaas actually had some great research in one of his many books that showed the temperature that occupants will find quote unquote comfortable and accept, depending on whether they can open their windows. And this is just super fascinating, right? Because you would think, oh, well, comfort is comfort. It's just a temperature. I always want it to be, 22 degrees or 21 or 20 degrees, whatever the number is. And what he found was that if people have access to natural ventilation and they can control airflow and get fresh air, even just that fact, that act, will allow the building to be 5 to 7 degrees warmer inside. Imagine how much less cooling load you need if your building can now be 25 or 27 inside. And people are happy as can be. They're productive as can be. Everything is good. No complaints, no fuss, no muss. But because they can open their windows, they will tolerate that. If 30 is still warm, okay, 30 is still warm. But if you can the difference on your mechanical loads at 25 or 27 versus 20 or 22 is huge. And now compound that over months, years. The difference in carbon, the difference in utility costs, the difference in you name it, by just being able to open windows is night and day. And this is again one of the passive principles to again reduce the stress, reduce the reliance on mechanical systems. And number 4 is daylighting. So incorporating daylighting is reducing the need for artificial lighting. So this saves energy. It also enhances, again, well-being and productivity. There's no replacement for natural light. I don't know how you guys do it in Vancouver sometimes with how cloudy it is. Here in Alberta, even though it's snowing this afternoon, it'll be sunny for sure. It's always sunny here. It's always sunny in Philadelphia and in Edmonton. But the intelligent placement and sizing of windows and curtain wall and sort of glazed facade elements is critical to successful daylighting. And in general, the performance of these systems is much higher than it is on typical buildings. Again, while we're still maximizing daylighting, we're not there's not too much of a sort of efficiency cost when it comes to the insulation values. So the passive principles are to, yes, optimizing the kind of sort of daylighting openings that we have, but also to make sure they're really high performance, so that we're not, because every one of those sort of building envelope sort of penetrations, yes, it allows in daylight, but it also is always kind of the weakest part of our thermal envelope. So we want to optimize our buildings. When it comes to glazing, the sort of consensus, as it were, is that regulation is going to drive change, essentially. I think for the majority of buildings, I think that makes sense, right? I think that's kind of always the way that the industry has gone, historically speaking, is that there's always been leaders. Those are the ones who are achieving the voluntary standards, the LEED Platinums, the passive houses, the net zero carbons, and then there's the floor is brought up as the ceiling is raised, right? So as people see what's possible, the regulatory bodies have increasing confidence and to say, oh, okay, it's possible, the industry is ready, to do this. We can sort of push people a little bit further than they would go otherwise. I think that's broadly what happens. I think there are exceptions to that, quote unquote rule. I think, something like the Massachusetts stretch code, it basically went from the equivalent of BC Energy Step Code, 1 to Step Code 5, not in 15 years, in 1 year. That's an example of, really ambitious regulatory push, just sort of throwing the market into a little bit of disarray, and in the short term, but I think in the long term, really moving things forward, and really accelerating what's possible. So I think that's I think we see both approaches, but I think that's kind of a unique approach. Let's talk about fiberglass, the advantages of fiberglass. So all of which we've talked about, all of the things that a high performance building facade has to do, which is a lot. And then there's everything that all of the passive principles. And so where do the materials sort of come into this? So we're asking our building facades to accomplish a lot, frankly, and increasingly amount. And so particularly our windows and curtain wall, which again are always going to be, no matter how good they are, they're always going to be the weak link thermally speaking. And so we have a few different materials to choose from. Some are better suited to our current and future requirements, and some are less so. Since the 1950s, we've seen huge improvements in glazing technology. We've gone from single glazing to double glazing to triple glazing, quadruple glazing, low-E coatings, argon, films, vacuum insulated glass, warm edge spacers. The kitchen sink has been really thrown at glazing innovation. Meanwhile, framing materials, which are what holds the glass in place. So if the glass is kind of being held here, the framing material is the exterior cap of our curtain walls, the interior frame of our curtain walls. The glazing is kind of going in the middle vertically. The framing technology has broadly stood relatively still because it's mostly been aluminum, and aluminum has been the most common commercial choice for curtain wall, for window glazing, because it's been really the easiest and the cheapest choice. And especially in the sort of post-war era, you can make a wide variety of shapes with it. It's relatively light. It's relatively easy to work with. But as we aim for more sustainable, durable, efficient building facades, we see that there's considerable room for improvement in a lot of these categories. And so of the advanced material options out there, whether we're looking at, wood or steel or, other, carbon composites, for example, really fiberglass in particular has emerged as the superior choice for its vastly better thermal performance, improved durability, lower environmental impact, so much lower embodied carbon, and as a result, its overall future-proofing capacity. So for thermal performance, this is an easy one. Even amongst the metals, aluminum is one of the most conductive materials on the planet. It's actually comparable to copper, and we use copper for wiring. It's amazing that we use aluminum as a building envelope as extensively as we do. Fiberglass, by comparison, is 99% less conductive. 99% less conductive than aluminum. This results in dramatically less energy loss through the building envelope, reduced utility costs, and even reduced condensation risk with fiberglass. So by effectively insulating the building with fiberglass framed systems, we maximize energy efficiency through all of these seasonal temperature fluctuations, through the increasingly sort of wonky climate that we're seeing, and reducing the stress on our expensive mechanical systems. In terms of durability, fiberglass is fantastic in this domain as well. So unlike metals, fiberglass is immune to corrosion. It's immune to moisture damage, and it's immune to the effects of salt and many cleaning chemicals. And this resilience makes it ideal for the challenging environments that we're facing, and whether those are swimming pools and healthcare, sort of facilities that are very high humidity environments where corrosion really is an issue, whether it's actually even some industrial applications, where you have to constantly wash the inside of the facade with, heavy cleaning chemicals, for example. Using fiberglass can dramatically reduce the maintenance needs and extend the service life of the windows or the curtain wall. From an environmental impact perspective, fiberglass is one of the lowest embodied carbon building materials in the industry, and it has 2.5 times less embodied carbon than aluminum. Aluminum is a very high embodied carbon material. Obviously, concrete, is number one, but really the metals and aluminum will be right behind that when we're looking to minimize our embodied carbon impact as well. And that really, the embodied carbon impact is really the impact from manufacturing. So it's not just, how much energy are we using throughout, the building's life cycle once it's in operation, which is an undefined amount of time. We don't know exactly how long a building is going to last, but we do know what it takes to build that building in the first place, right? And that's the embodied impact. And that's an impact that's realized very quickly, right? So a building is put together in a couple of years, and then of course it lasts, many, many decades. But as we sort of build, higher and higher performance building envelopes, the proportion of the embodied impact to the operational impact actually starts to tip towards more embodied. So Robin had that great diagram of, that tall skyscraper that was 30%, embodied and 70% operational. Well, with, passive buildings, with higher performance building envelopes, it can actually switch, where it's even, is the preponderance of the environmental impact actually on the embodied side, because we're creating buildings that are so high performance, the operational demands are so low that actually all of the environmental impact is in the construction. And so to minimize that becomes more and more important as we get better and better building envelopes. And this will, of course, play, a role in sustainability for all of our buildings, and also for those clients, those architects, and those sort of leaders who are looking to differentiate themselves from the rest of the market. And future-proofing, lastly, of course, fiberglass framing helps buildings to meet and exceed current stringent requirements, and even the tightest energy codes. It doesn't expand, it contracts as much. It really maintains the same sort of profile as the glass that it's holding. Fiberglass is mostly glass after all. So with these exceptional thermal properties, low carbon impacts, and even low toxicity, make it an ideal fit for, Toronto Green Standard, BC Energy Step Code, Massachusetts Stress Code, LEED, Net Zero, and Passive House. So these are a lot of very tangible benefits, not the least of which is that all of this is made in Canada, right? That's kind of cool that we can actually, make high performance products in Canada, that we don't have to just import them from, other parts of the world. that we can create sustainable local jobs and sort of enhance our industrial knowledge and capacity here, and then even create export opportunities of this Canadian innovation. We don't just have to export Justin Bieber maple syrup and I don't know, Celine Dion or something like this, or Canada Goose jackets. We can innovate cool things. Like Canada has a lot of cool things, not or just oil and lumber or something, right? We can create real things, and we have talented people in this country. And a really standard example of this is, soft sales pitch here, Thermoframe 9 PH, which is the highest thermally performing curtain wall in the world, and the first curtain wall to be certified to the Passive House Institute. That's the German, Darmstadt, Germany's cold climate criteria, which is 0.60 watts per meter squared Kelvin, framing glass overall, which works out to a U factor of 0.11 or R9 overall framing glass. And this is along with the highest PHA plus efficiency class rating for air tightness and thermal comfort, as this globally recognized third-party testament states. And it's quite interesting. I mean, the Passive House Institute, talking about passive principles, what the actual Passive House Institute in Germany does quite uniquely is it certifies individual building components. And so whether or not you're certifying your building to Passive House standards, what you can see is a full directory of manufacturers who have had their claims verified by a trusted third party, which is quite unique, actually, amongst all of the other sort of accreditation systems of all of the other codes and regulations. Passive House is quite unique in certifying materials and components and systems, whether that's glazing, whether that's roof systems, whatever that is, to have it so that you don't have to just trust whatever. And manufacturers are trustworthy people. We're all doing our best, but still it's great to have that sort of external rubber stamp that says we've gone through, we've checked the math, and we made sure that these guys are actually selling what they say they're selling, and it performs how they say it's going to perform. And that's a big thing, because it's one thing to specify a material, it's another thing to actually get what you want and to have it installed properly. And that this is a Canadian product is all the more impressive. So fiberglass, as you can see sort of on these diagrams here, in these sort of different framing systems, we have our Generation 1 framing system and our Generation 2 framing system. And what we can see is a very flexible system. So there's a lot of adjustability that can be done in the glazing pocket. So to incorporate a lot of these new glazing technologies we were talking about earlier as well, and whether that's the smart electrochromatic glass, vacuum insulated glass, double glazing, triple glazing, depending on climate zones, integrated photovoltaic glazing. So all of these things can be done with fiberglass, and this really sort of sets the stage for the next generation of high performance building facades. And all of this is very exciting and very optimistic for the future, because it demonstrates industry leadership and commitment to sustainability for the manufacturers that are using fiberglass and leveraging this new material, as well as building owners who are installing it and architects who are specifying it. An example of this excitement and optimism is the new academic building at Concordia University of Edmonton, which will be the first in North America to utilize triple glazed vacuum insulated glass units, significantly enhancing the center of glass performance by 50% relative to even conventional triple glazing. And that's 300% better than double glazing. So this groundbreaking vacuum insulated glass system paired with our next generation Thermoframe 8 fiberglass framed curtain wall marks a significant milestone, and it will result in the most thermally efficient curtain wall ever seen in North America. And there's much more in the pipeline. What we're seeing from coast to coast to coast is an ever-increasing demand for fiberglass frame systems, particularly for institutional projects aiming for net zero, for LEED, but even increasingly these higher performance, BC Energy Step Code 5, Massachusetts Stretch Code, Toronto Green Standard, all of which are rapidly becoming table stakes, really, for new government buildings, universities, healthcare, and owner-occupied commercial buildings, where they're really looking at this payback period and they're really saying, okay, this makes sense because we're going to save all of this in the long term. We're going to future-proof ourselves against all of these potential future issues. This is a really, really smart investment. And so the fiberglass's really unique properties really do make it an exceptional solution for the challenges of high performance building facades in the 21st century. But of course, there's still no one size fits all. And so whether that's for building facades or for anything else, different climate zones, different building types, and of course, different clients pose different constraints on our design considerations. And we therefore have to tailor our approaches for each new building to each part of the world. So in colder regions, which is most of Canada, the primary concern for building facades is thermal performance and of course aesthetics. And here we can leverage those passive principles. And in this domain, fiberglass frame curtain walls excel for their low thermal conductivity and ability to offer higher window to wall ratios while still meeting the stringent energy codes and voluntary certification standards. Because if you just take the prescriptive path on a lot of these things, you'll end up with very small windows and not terribly attractive buildings typically. So when we exceed the standards, when we use better building materials, we can expand the sort of design possibility space, and we can design beautiful buildings and high performance buildings, and those need not be mutually exclusive. To address these, regional challenges that we face with building facades, fiberglass can do all of them. And whether that's with unique thermal breaks, glazing types, finishes, custom caps, fin, sunshade, solar panels, you name it, fiberglass has the ability to be customized to design beautiful, high performance buildings that respond effectively to their local environments, enhancing building performance and value from day one. But yes, I'll just answer the question from Abdul here. Whether this building facade improvement makes good business case for an existing building, it really depends on the condition of the existing facade, right? If the existing facade is shot, if the framing is not in good shape, the glazing is usually the first to go. Once the glazing is the first to go, the best bang for your buck is usually just to replace the glazing. You can just get better glazing. If you're using 40-year-old glazing, getting brand new glazing will do wonders for most buildings. If the building isn't in great shape, if the framing isn't in great shape, yeah, you could make an even bigger difference. You can double the difference, again, with fiberglass framing. So it really depends on kind of what the existing building situation is. How good is it? How bad is it? What are the needs of that building, etc. So number two is your system a standalone facade or can be incorporated into other facade systems as a subcomponent? Yeah, a curtain wall really is it interfaces with the opaque parts of the building assembly, but it is its own standalone system. So the glass curtain thermal frame systems are framing glass systems with flashing and anchors and everything that will tie into the structure and will then tie into their neighboring sort of facade components, which will be the opaque parts of the assembly. So it really is its own sort of standalone component. And of course, it can incorporate other subcomponents. It can incorporate different kinds of glass. So the glass in this case would be a different kind of subcomponent. And so that would be, whether you're using double glazing, triple glazing, vacuum glass, what have you, that would be the subcomponent. But yeah, the glass curtain systems are really standalone systems.
Well, I think I have everything covered. We still have still a good amount of people in the audience, but I would say, yeah, Peter, thank you for presenting today. Also, thank you to the audience. And if there's still any questions, feel free to contact us and have a nice rest of your day.